Hello, my wonderful students. How are you doing today? Hope you are fine. Thank God for that. This is your physics teacher, Asaga Prince Chinebompa. I know you must have gotten your scheme of work, the SS1 students. We want to have our normal class today. The other classes we've been maybe romancing with SS2 and SS3. Today, I want to be with you, my wonderful SS1 students. We are going to treat electric field. I believe you've gotten your scheme of work. So we are going to discuss electric field. Electric field. At the end of this particular lesson, it is expected that you should be able to define an electric field and explain an electric field intensity. It's also expected that at the end of the lesson, that you should state the unit of electric field. And at the same time, it's expected that you should mention and explain the types that we have in electric field. Define the potential difference between 2 points in an electric field. It's also expected that you should define electric currents and at the same time mention the different types of electric currents. So, having known what is expected of us to do in this particular lesson or what we should know in this lesson, let's keep the ball rolling. What is an electric field? An electric field is said to be a space or a region in which a charged body experiences a force. A space or a region in which a charged body experiences a force when that charged body is brought into the field. So we say that for the fact that this charged body is going to experience a force when brought into that particular space or region, which we refer to as the electric field. We now say that an electric field is a vector quantity. You know very much or very well what we mean by vector quantity. That is the physical quantity that has both magnitude and direction. Which means there will be a direction in that particular field, and when this body is being placed inside the field, then a force will be acting on this particular body. And then we are saying that this particular body should not just be an ordinary body. It should have positive charge. So the charged body would now be a positive charged body. And then when this positive charged body is brought into this particular region or field, now which we call electric field, it will now experience a force. The direction of this field is the direction of the force, which we are now going to see within a space of time. The magnitude of this particular electric field we are talking about is known as electric field strength or electric field intensity. We call it electric field strength. Electric field strength or electric field intensity. Electric field intensity. That is the magnitude. When we talk about the magnitude, we are talking about the strength. How large, how big is it? That is what we mean by the magnitude. So we are saying that this particular electric field intensity or electric field strength, we can now define it as the force per unit charge acting on a small positive charge, as I told you. it is now defined as the force per unit charge acting on a small positive charge placed at a point inside the field. It is mathematically given as, that is, the electric field intensity is mathematically given as E is equal to force per unit positive charge, where F there is the force, and then plus delta Q is this positive charge, where E is the electric field intensity. The unit of electric field is Newton per coulomb. The unit of electric field is Newton per coulomb. Newton per coulomb, which you now say is NC raised to power minus 1, or you say N/C. That is how we write our Newton per coulomb. We can as well measure electric field with a unit volts per meter. Electric field can be measured in the unit volts per meter. Volts per meter. Per meter. That is Vm raised to power minus 1 or V/M. So it's either you say that an electric field is being measured in volts per meter, or you say that an electric field is being measured in Newton per coulomb. Having known what electric field is all about and the unit of electric field, let's now see types of electric fields. Types of electric fields. Types of electric field. Types of electric fields. So we say that there are two basic types of electric field. There are two basic types. One is what we call the uniform electric field. Uniform electric field. And the other is what we call the variable electric field. These are the two basic types of electric fields that we have. So let's see these two types and then try to see how we can now identify them. Uniform electric field. A uniform electric field is that field in which all the field lines are straight. That is that particular field that you see that all the field lines are straight. That is, there is no maybe rigorous part, they just move parallel to each other. So that is how we indicate uniform electric field. All the lines are straight. They are parallel to one another or to each other as the case may be. Now when we talk about variable electric field, we say that this is the type of field in which the field lines are curved. The variable electric field, the field lines are curved, while uniform electric fields, the field lines are straight. They are parallel to one another or to each other. So when we come to variable electric field, we say that the electric field on these lines are those ones that are tangential to the curve. They are tangential to the curve as far as when you now try as much as possible to present them. And then how do you see them? Is only when these lines that are tangential, the direction of this particular line gives you the electric field point, as the case may be. So how do we see this variable electric field? As we say that they are curved, so they are now curved in this way. And we now say that at any point on time at any place on this particular curve, that you now see this particular particle or the charge, where the arrow is pointing gives you the direction of this particular field. So if it's at this point, the direction is pointing here, that gives you the electric field. If we have here to be point A, point B, and point C, it's now telling us that the direction at point A is straight. The direction at this particular peak point is also pointing at that particular direction, while at this point C is pointing downwards, telling you that the direction varies, it's not straight. That's why we call it variable electric field. All right, having seen these two fields, there are some other things that you need to know as far as electric field is concerned. So what are these things that we need to know, especially the parameters that are being involved? One is what we call the potential difference. Another one is the electromotive force, and then the other one is the electric current. So let us now see to a little subheading: potential difference, EMF, and electric current. Potential difference, potential difference, potential difference, which we refer to as the PD. And then we have the electromotive force, electromotive force, which we now say is EMF, and electric current. So let's now see to this particular sub-headings and see how far we are going to treat them. So let's start with the potential difference. The potential difference, PD. The question is, what is potential difference? The potential difference between 2 points in an electric field is the work done in moving a positive charge of one coulomb from one point in the field to another point. I repeat, the potential difference between 2 points in an electric field is the work done in moving a positive charge of one coulomb from one point of the field to another point. You can agree with me that in our first term work, as well as our second term work, we say that work is done when a force is being applied to a particular body and it causes this body to move a certain distance. So that gives us the mathematical relationship of work, force, and distance to be W is equal to FD, where F is the force and D is the displacement. So when we now apply for the fact we say that this particular charge body, when brought into a region where it will now experience a force, definitely this particular body is going to leave that particular point and move to another point as far as force is being applied. For the fact that force is being applied to it and it leaves that particular point and moves to another point, we say that work is done. And that work that is done is what we refer to as the potential difference between those 2 points, from one point to another. And then I told you that this particular charge body must be a positive charge body and not a negative charge body. So we say that the potential difference is an essential condition for the flow of current in an electric circuit. So if there is no potential difference, there will be no flow of current in this particular circuit or in an electric field. Because this particular potential difference is now a force that is being applied to this charge body. And then when it moves from one point to the other, then we now have electric current. That is exactly what we are trying to say. So in all these situations, we are saying that an electric circuit is a part because this particular charge is moving around this particular field. And then we now term this particular field to be a circuit. So what do we mean by this particular circuit? We say that an electric circuit is a path, and this path is P-A-T-H, is a path, traced, or a path that we provide in which electric current, or we say that is electric charge or electric electrons, where they now flow. So when this particular force acts on this particular charge body, it will now move from one point to the other. And then as it's moving around this particular field, we said that this particular field now is a circuit. And then this particular circuit we are talking about, we say that is a path that is being provided where electric charges flow. It's just like we see our main road, or we say our third road, is a path that is being provided where vehicles now ply. What of the rail lines? Is a path that is being provided where railway trains do move. So likewise, electric circuit is a path that is being provided where electrons or electric charges, where they flow. So we said that for an electric current to flow in an electric circuit, there must be an electric pressure between the ends of the material, or between the ends of the field. So this particular pressure we are talking about, I told you, is the potential difference, which we are going to see. And then in an electric field, we know that it's not just a place where we are going to play football. Like when we ask so many of you, what do you mean by field? We said that a field is a place where maybe Chelsea, Manchester United, Man City, where they go and play football. Yes, you are correct. It's still a field. Where we still say that athletes perform their duties. Fine, you are good. You are very much correct in saying that. But in this situation, the field we are talking about comprises at times our wires, where we now assemble our wires together. That is our metals. Then electrons will now flow around it. That is our electric field. We can also create it using electrolyte. That is our acids. When we now dissolve them or put them in a container, they now serve as our voltmeter and then try to dissociate. And then at this point of time, electrons will still flow in forms of ions. So having known that electrons flow around a circuit, and then what do we mean by this particular circuit as we've just defined? And these electrons, which we now call them the charges. We said that there's a pressure that actually acts on this particular charge, which actually causes the charge to flow around or to move from one point to the other. And then we said that this particular force that actually pressurizes it, as I told you, is known as the potential difference. So the unit of the potential difference is the volt. The unit of the potential difference is the volt. That is capital V. Mind you, volt is not necessarily a unit. It's someone. So this is a scientist that has actually worked on this particular electric field. And then he came up with something reasonable. And now they said, instead of this particular thing, trying to name or bring out a unit for this particular work you've done, we are now going to give that particular work, the unit should be volt. So that's how volt became the unit of potential difference. Then the question is, what is this volt? What do we say is volt? So I want to define volt for you. The volt is the PD, or you say is the potential difference between 2 points on a conductor when 1 joule of work, and that joule is Joule, is still someone's name. When 1 joule of work is done in moving 1 coulomb of charge, from one point to another. Let me repeat that definition again. The volt is the PD, PD means potential difference, between the 2 points on a conductor when 1 joule of work is done in moving 1 coulomb of charge from one point to another. Then coming to that, what is joule then? What is joule? We say that is someone's name. At times when we ask our students or you students what is joule, you now tell the joule is the unit of work. The joule is the unit of energy. No. It's someone that worked on those things and after which this particular area is being named after him. Like this Volt. You've seen that Volt worked on electricity and then tried to discuss or try to defend himself before the scientists. And the scientists agreed that the unit should be volts. So what is then joule? We now say that the joule is the work done when a force of 1 Newton is being applied to a body and it causes that body to move a distance of 1 meter. Let me define it again. Joule is that particular work done when a force of 1 Newton is being applied to a body and it causes that particular body to move a distance of 1 meter. That is joule. That is telling you that 1 joule is equal to 1 Newton multiplied by 1 meter. So which means joule is equal to Newton per Newton meter. That is the joule. So when we now have a look at work done is supposed to be Newton meter. But for the fact that this young man actually performed some researches and then after which he defended this particular work that he did, and now said that the unit of work should now be what? Joule. That's how it came about. So when you are being asked to define joule, you now say that the joule is the work done when a force of 1 Newton is being applied to a body and it causes that body to move a distance of 1 meter. Electromotive force, EMF. Electromotive force. So what do we mean by electromotive force? We said that the electromotive force of a circuit is the work done in moving 1 coulomb of electricity around the circuit. We say is the work done in moving 1 coulomb of electricity in the circuit. We can also define EMF, which we say is the electromotive force. We say that it is the energy per unit charge. Energy per unit charge moving through a cell or a battery. Energy per unit charge moving through a circuit or this particular battery, a cell or a battery. Now when we come to this particular EMF, like at times WAEC or NECO will ask you to define EMF. They look at one particular thing which you must tell them. Now just get a battery. Before I define it, let me demonstrate. Let's just go and buy a battery, a dry cell, either your Tiger Head or Panasonic or any other one. Just buy the battery. Then bring the battery out from the cellophane that they use and now wrapping it. You look at the body, you will see that on the body, you see where they wrote 1.5 volts. 1.5 volts. It's now telling you that this is the EMF of this particular battery. That is the total work that is going to be done when electrons are to, or when charges are to be moved from one point to the other. So when we now define EMF, we say that it is now that particular potential difference across the terminals of a cell when the cell is not delivering any current to the external circuit. I repeat, the electromotive force of a cell is that potential difference between the terminals of a cell when that particular cell is not delivering any current. That is, when you now buy this battery, you've not used it at all. The whole thing is there. No reaction has taken place in it. So the whole magnitude of the work that is to be done there is referred to as the EMF. And then the value is 1.5 volts. That is what EMF is telling you or is all about. So what is this EMF doing in an electric circuit? An EMF causes a potential gradient, a kind of pressure in this particular electric circuit. An EMF causes a potential gradient to occur along a conductor or in an electrical circuit. It now pressurizes these particular charges to move from one point to the other. That is exactly what we mean. Because if this is not there, these particular electrons will still, or the charges will still remain there. So because of it, we now say that the EMF of a cell mathematically is EMF is equal to work done, which we say is W, all over charge. All over charge, Q. So EMF is equal to W all over Q. That is the work done per charge. So when we now see all this now, the unit of EMF is still volts. This young man still works on it, which means work all over charge is equal to volts, as the case may be. So when we want to determine the charge, we now say that the charge Q is equal to the charge or the work done. If we want to determine the total work done from this equation now, we cross and multiply, in that we are going to have work done is equal to charge multiplied by the potential difference. That is the total work done, the charge multiplied by the potential difference across the terminals of the circuit. So that is what we mean by the EMF. So we are saying that the EMF now, in terms of our cell, as we said, what is the EMF of a cell? I've already defined it. I've already told you what it means. So the electromotive force of a cell is the potential difference. The electromotive force of a cell, that is the EMF of a cell, is the potential difference between the terminals of the cell when the cell is not delivering any current to the external circuit. When this particular cell is not delivering any current to the external circuit. It is the source of power, as I told you, which must supply the energy in moving the charges. It is that force that must pressurize this particular charge to move around the circuit. All right. So having known what we said about our EMF and our potential difference, let's now see the last part of it, which we now said is the electric current. What is electric current? An electric current, which we now identify or symbolizes with a capital letter L, electric current is defined as the time rate of flow of charge through a conductor. We say that it is the time rate of flow of charge through a conductor, which means I is equal to Q over what? T. The time rate of flow of charge through a conductor. Electric current is in an electric circuit. Electric current in an electric circuit is as a result of the motion of free, or you call it mobile electrons. So when you now talk about electricity or the electric current or electrons, it's as a result of the movement of the electrons in the metallic conductor. Now we call them free or mobile electrons. So when they move from one point to the other in that circuit where you wire your house, so your house that is being wired constitutes electric circuit. So the movement of these electrons from one point to the other is now what you refer to as the electric current. Now, how will this electric current come? There must be an EMF. There must be an EMF. And what is this EMF coming from? Think about your generator. That gives you the gradient. That gives you the force that drives these electrons to move out and then give you light. So your generator serves as a source of power, and then that serves as your EMF that pressurizes those electrons or those charges to move from one point in the field to another point. All right. So now we have different types of electric current. Different types of electric current. So that is our subheading: types of electric current. Types of electric current. We said that there are two basic types of electric currents. I repeat, there are two basic types of electric currents. The first one is the one we refer to as the direct current. One is direct current, which we call the DC. And the other one is the alternating current. Which we call the AC. So how do we know these types of currents, or how do we identify them? So let's have a look at the direct current, the first one. The direct current. The direct current, DC, in brackets, electricity, that is the direct current electricity, is one that is always in the same direction. It's one that is always in the same direction. It moves constantly. It doesn't change. Its intensity or its magnitude do not change at all. So it moves in the same direction. It does not fluctuate in its intensity, as I've just told you. It doesn't fluctuate. The intensity doesn't change. It's always steady from the beginning to the end. It is the type of current that is obtained from the battery, which serves as a source of potential difference. A type of current that when you buy your dry cell battery, maybe you put it inside your transistor radio or inside your torch. Those days that you have torch batteries. So if you put it inside your torch, then it just gives you light continuously as it is, unless that particular cell dies down, or unless your radio stops, you now go and check and see whether the battery has died down. But if not, the magnitude or the intensity of this particular current is always like that throughout. It doesn't come forth and go backwards. That is what we call fluctuations. All right. So as far as this particular current is concerned, it is the type of current that you receive from our generators in our houses. You discover that when you now on your generator, that definitely the light is steady until you off your generator or the petrol inside the generator finishes. So it does not fluctuate. The light is always steady from the beginning to the time you will now off your generator. So electricity from your generating set is a direct current, and electricity from your torch batteries or from any of the batteries is also referred to as your direct current. So let it be established in our mind that electricity now that is coming from our generators is a direct current. So actually we said that the battery has a force called the electromotive force, as I've already told you. Likewise, your generating set, it has a force which we refer to as the electromotive force. What is the work of this? This electromotive force enables these particular charges to be maintained, or it maintains the flow of charges throughout the circuit. That is the work of this your generating set, or the work of the battery. The intensity of flow of light is always steady. It maintains the flow of current throughout the circuit until you off your generator. So that is the work of the EMF. It enables this particular current to flow, or it also maintains the flow of charges through the circuit. So direct current, as I've told you, is very, very good as far as our homes and our industries are concerned, because they are always steady. The intensity is always steady. It doesn't fluctuate. So we can now use it to do whatever we want to do at any point of time. It doesn't disappoint. It doesn't come forth and goes backwards. It's always steady at any point on time. And I've told you that typical examples are the current you receive from your battery, your dry cell batteries, or even your alkaline batteries, and the ones you get from your generating set. That's what we refer to as our DC current. So let's see the second one, the alternating current, which we call AC, or the alternating electricity, which we refer to as AC. The alternating current or the alternating electricity is one which fluctuates. Is one that fluctuates. What do you mean by fluctuation? Is one that fluctuates. Is one that fluctuates. That is, it comes forth, goes back. It comes forth, goes back. It's not steady at all. So that is what we mean by fluctuation. Is the one that fluctuates or reverses periodically. Or reverses periodically. It reverses periodically. It's one that fluctuates or it reverses periodically. As far as the intensity is concerned, so it doesn't flow at a steady rate. It fluctuates from time to time. So we are saying that an alternating current is one which fluctuates or reverses periodically in its intensity of its flow of what? Current. It's one that fluctuates or reverses periodically in its intensity of its flow of what? Current. That is what we mean by an alternating current. It is the type of current that is obtained from the mains. It is obtained from the mains. M-A-I-N-S. From the mains supply from the electricity transmitting station. It is obtained from the mains supply of the electricity transmitting station. Typical example is the light that we receive from the EEDC. The light we receive from the EEDC. That is Enugu Electricity Distribution Company. You see that when at times they now give you light in your homes, if you watch that light, you see that it's not steady. It will fluctuate. At times it comes forth, and the other one it goes backwards. So the unit of electric current is the amperes. The unit of electric current is the amperes. And then I've told you that electric current is the time rate of charge. That is, I is equal to Q all over T. So we have a little thing that you need to do. This is a mental work before I give you the assignment, so you can now try as much as possible to determine the total quantity of work done in an electrical circuit in driving 50 coulombs of charge from one point to another in this particular circuit. Determine the total quantity of work done in an electric circuit in driving 50 coulombs of charge from one point to another in the circuit in 5 seconds. In 5 seconds. So this is what we have done. So in summary so far, we've been able to define electric field, and we say that an electric field is a space or a region in which a charged body experiences a force. It is a space or a region in which a charged body experiences a force when that charged body is brought into that particular region. We've also been able to establish a fact that electric field intensity is the force per unit charge acting on a small positive charge. We say that is the force per unit charge acting on a small positive charge placed at a point in the electric field, which will give you the equation as E, which is the electric field, capital E, is equal to capital F, which is now the force, all over positive delta Q. Positive delta Q is the small positive charge. I also told you that electric field is of two types. Electric field is of two types, and we say one is what we call the uniform electric field, which has the field lines parallel to each other, that is the move straight. And then the other one is a variable one, which has gotten a curved line. In the variable, we say that the direction of the field gives you the direction of the electric field. I further told you that the potential difference PD between 2 points in an electric field is the work done in moving a positive charge of one coulomb from one point to the other. The potential difference between 2 points in an electric field is the work done in moving a positive charge of one coulomb from one point to the other. And I told you that the SI unit of this particular potential difference is the volt, or is the volt per meter or Newton per coulomb. We try as much as possible to define the volt, and I define the volt as the PD between 2 points on an electric conductor when 1 joule of work is done in moving one coulomb of charge from one point to the other. That is the work done when 1 joule, when it is, I said that the volt is the PD between 2 points on the conductor when 1 joule of work is done in moving a coulomb of one charge from one point to the other. Finally, I also told you that the electric current I is the time rate of flow of charge through a conductor, which is mathematically given as I is equal to Q over T. The two types of electric current, as I told you, are the direct current, which doesn't fluctuate. Its intensity is steady from the beginning to the end. And typical examples are the current you receive from your generator and your batteries. And the one that is one coming from our friends that call themselves EEDC people, the light that we receive from them, which we refer to as the alternating current. Those ones fluctuate. The intensity is not steady. It may come forth and go backwards at any point in time. So the intensity decreases. So the unit of our electric current is the ampere. And now I define the ampere by saying that it is the quantity of electric charge flowing through a section of a conductor in 1 second. I repeat, the ampere is the quantity of electric charge flowing through the section of a conductor in 1 second. Alright, before I will now let you go at this point in time, please take down these assignments. 1. What do you understand by electric field and electric field intensity? What do you understand by electric field and electric field intensity? 2. Define the potential difference between 2 points in an electric field. The potential difference between 2 points in an electric field. 3. Define the following quantities. A. volt. A, volt. B, ampere. And finally, number 4, differentiate between AC and DC. Differentiate between alternating current electricity and direct current electricity. So, I still remain your physics teacher, Asaga Prince Chinebomba. Remain safe, and God bless you. Bye for now.